Okay, so this is the final topic really of our A-level chemistry course. In most textbooks, it'll be a separate chapter, but I think for us really it's the culmination or the final part of the whole transition metals topic, which has been a very large topic. So it's important to remind ourselves about some of the complex ions. So we've just got a very straightforward complex ion here. We've got a central copper ion. There are 6 water molecules coordinately bonded to that copper ion. So we've got 6 ligands. This means the 2+ charge is now more widely distributed across the whole complex ion. So we have a more stable species. So one thing that we've got to have very clear from the outset is what exactly does AQA expect you to know, because every exam board will have a slightly different set of metal ions that you need to know the colors of, or you need to know the products if they react with certain species. And so AQA have clarified that. We've got these this slide and the next slide, and they really sort of detail what it exactly is you're expected to know. If we look at the top of this page, it does mention about substitution reactions involving cobalt-2 were previously required under the old A-level chemistry spec. So what that means is if you see some, you might see some exam questions which feature cobalt, and they are almost definitely exam questions from the previous specification. It says these reactions and the colours of the solutions and products are no longer required for the current A-level chemistry specification. I will just caveat that because I think you do need to know about ligand substitution, and one of the ways that you could identify that is through a change in colour, and they have done it, I think, with cobalt once. So it's not that you're necessarily expected to know the colour, but you probably are expected to know that if there's a change in colour, that's going to involve, judging by what's been added, possibly a ligand substitution reaction. You'll also notice that it has the 4 colours for the 4 different oxidation states of vanadium. So there are 3 principal types of reaction regarding metal aqua ions. By far the largest, and I stress this because it can sometimes be easy to miss, as we'll maybe see, or hopefully see, is hydrolysis. So the vast majority of the reactions of metal aqua ions that we're going to look at are actually going to involve hydrolysis. There are some regarding the substitution of ligands. They're typically actually easier to spot once we've ruled out hydrolysis, that is. And then finally redox reactions, where that would obviously have to involve a change in the oxidation state of the metal. So we're going to look at a series of hydrolysis reactions regarding metal aqua ions. They are principally the same thing, although they may initially appear to be different. So hydrolysis here means breaking an OH bond in one of the water ligands to produce an H+ ion. So we can see that's what's happening. If we look, there's the hydrogen of one of the water molecules, and it is released. We can also see that it's an equilibria reaction. We can also see that different charges on the ion result in different pHs. If we look at this table here, that shows it quite clearly. So a metal 3+ ion, or aqua ion, is more acidic than a metal 2+ aqua ion, and that's going to become important in one of the reactions later on. So we have a very positively charged metal ion at the centre. What that leads to is the electron density from the lone pair is attracted more closely to that metal ion. So the lone pair, that's on the oxygen, the one that's forming the coordinate bond. That's going to draw the electron density in the OH bond even further or even closer to the oxygen. That's what we're trying to show there, which means that we end up with an even greater delta positive charge than we might otherwise have had on our hydrogen, and the bond is now easier to break. So, but it is an equilibria, let's not forget. So this page is showing us the first equilibria, the second equilibria, the third, fourth, the fifth, sixth, etc. Notice that the species in red doesn't have square brackets, so it doesn't have any overall charge, which is why it doesn't have the square brackets. But also it's in red because this is the precipitate that we're going to see in some of the different reactions. So because it's no longer charged, because the complex itself, is no longer charged, or has no overall charge, it isn't able to dissolve. We don't get the trade-off in electrostatic forces of attraction. So normally if you're dissolving something in water, you're breaking or disrupting hydrogen bonds. So if it's to actually dissolve, you need a payback, you need new electrostatic forces of attraction formed, and that's typically from a charged ion. If you remember from the thermodynamics topic, where we drew a charged ion, and we knew that this would be then surrounded by water molecules, almost like a cage. I'm only going to draw some of them, I'm not going to draw all of them. And we had, as a result, new electrostatic forces of attraction form. So we may have been breaking hydrogen bonds, but we were getting energy released from the formation of new electrostatic attractions. Well, in these species in red here, the one that I've underlined with the yellow, there is no charged particle now. There's no charged species. So now there can be no new electrostatic attractions formed with water molecules, and so it cannot dissolve in the water. So we have the precipitate. So that is why we're going to see the precipitate shortly in these reactions. And this is just a very similar slide to the one before. The one prior to this involved a 2+ complex ion. This one is starting with a 3+ complex ion. There is no real difference. It's still equilibria. It just means that we have a decrease. We've got we can go from 3+ to 2+ to 1+, and then we get the precipitate formed. There it is again. Now the hydrolysis we've just considered, which has been reflected in the pH of the different metal complex ions, can actually be well, that equilibria can be like anything. We can shift things on the equilibria. We can shift things to the right or shift things to the left. And so we can encourage that hydrolysis if we add a species such as hydroxide ions. So we're starting with the iron hexa-aqua ion. It's a Fe2+, so iron 2. If we add that hydroxide, I think the impression can be that there's been a ligand substitution because we have 6 water molecules on the left around the iron. On the right we have 4 water molecules and 2 OHs, and we have added 2 OH minus ions to that original iron hexa-aqua ion. But this isn't a ligand substitution. This is really important. What has happened is the OH minus ions have taken or stripped off the H plus that was produced by breaking one of the OH bonds in one of the water ligands. So this is not a substitution reaction. We have not substituted a water molecule for an OH minus ion. We have just encouraged the breaking of an OH bond in a water molecule. And you can see that we get, in this example, a green precipitate. And again, it's a precipitate because there's no overall charge, so it can't dissolve in the water. We don't have the square brackets because it's not a charged ion. It is a complex, that's true. If we left it over time, this green would change to brown. And if you notice in the bottom box, you can see that actually that also means the precipitate's still there, but now we've got another water molecule has become an OH minus ion. So again, it's just further hydrolysis essentially. Here's another example. And this really also shows why this topic is treated separate to transition metals, because actually we're looking at something that isn't a transition metal here. We're looking at aluminium, but it is an extension of what we've been doing. Again, this is a hydrolysis reaction. We start with our 3 plus metal hexa-aqua ion. The hydrolysis takes place because we add hydroxide ions, forms the precipitate, a white precipitate, because this is not a transition metal. Again, it's a precipitate because there's no overall charge on the complex. But in this particular case, in the case of aluminium, we can then add excess or more hydroxide ions. So we would have added them up previously drop-wise, and that would have resulted in a precipitate, and then we could add excess hydroxide ions, and we actually then get the precipitate redissolving or dissolving because we take the hydrolysis another step. We end up with an overall complex ion with a 1- charge. We've now stripped off, in effect, 4 H+ ions from 4 of the water ligands. And this just summarizes. So the actual test, and it's very important to just recognize that, is when we are adding the hydroxide ions to these metal hexa-aqua ions, we are doing so drop-wise. We will get the precipitate. If we then added excess, in all cases except aluminium's, there would be no change. But in the case of aluminium, we would get further hydrolysis and we would see the aluminium redissolve. So remember the hydrolysis that we've seen, it was at equilibria, and we could shift that equilibria to the right until we got a precipitate by adding hydroxide ions. But then, so that also suggests, well, what about if we added H+ ions? What would happen there? So if we have our precipitates, we've got our copper precipitate and our iron 2 precipitate and our iron 3 precipitate. If we had H+ ions, we can shift it back to the original metal hexa-aqua ion. So that's what we're doing here. We're adding excess H+ ions and returning back to the original hexa-aqua ion. In the case of aluminium, we can do that also. All right, so there's our aluminium. We can add excess H+ ions and we can get back to our hexa-aqua ion. But equally, if we added excess OH- ions, we could extend the hydrolysis or take the hydrolysis further. So what this is sort of highlighting or showing is that the transition metal complexes, the ones that are, when they're in a precipitate form, they can act as bases because they can accept H+ ions. In the case of the aluminium precipitate, and this is something you also saw, there's a feature of aluminium that you saw in the oxides topic, is that it can act as both a base and an acid, so it can accept protons or it can donate protons, so it is amphoteric. All right, and that's something to bear in mind when thinking about the aluminium complex ions. So on the surface, if we're adding NH3+, our thinking might be that we're doing a brand new reaction, or we're doing something different to what we've been doing before, but actually it's still hydrolysis, and all we are doing is affecting the position of equilibria. So if we add ammonia, which is a base, and we think about those equilibrias we saw earlier with H+ ions on the right hand side, if we remove those H+ ions, we shift the equilibria to the right. So the NH3 here is acting in the same way as the hydroxide ions acted earlier, and we are just encouraging the hydrolysis of these metal hexa-aqua ions. So I'm showing the iron 2 hexa-aqua ion, and it's the same precipitate. It is the same color. It is the same formula for the precipitate. It is more clearly hydrolysis here because we can see that the H+ ion has been accepted by the ammonia, by the lone pair on the ammonia to produce ammonium ions. But we have got exactly the same reaction. So adding OH- ions, adding NH3 molecules, ammonia molecules, they are performing the same function. They're accepting protons, and they are shifting the equilibria, in the hydrolysis equilibria, to the right until we get a precipitate formed. However, there is one exception. So initially, when we add ammonia, and we would do that dropwise to the copper 2+ hexa aqua metal ion, we will encourage the hydrolysis. We will shift the equilibrium to the right. We will end up with our blue precipitate. But then, if we add excess ammonia, this is the one complex ion in which we now get ligand substitution. So we do then replace the 2 hydroxide ions and 2 water ligands, so the hydroxide ligands and the water ligands for ammonia to get this complex ion that we have at the end. So we get a precipitate formed, we add excess ammonia, we get ligand substitution, and the precipitate dissolves, and we get a deep blue colour. And the deeper blue is because we have actually changed the ligand. So remember, there are various factors that affect the colour of a transition metal ion, but one of them is the type of ligand, and that's exactly what we've done. We've changed the type of ligand, so even though it's blue, it's a much deeper blue, and we have got a different energy gap between the d orbitals that result in a different wavelength of light being absorbed, and so we get a different colour being seen. And just a reminder that the ammonia is being added dropwise, and we keep doing that, and the exception, the anomaly, or however you want to think of it, is copper. So we now consider the reactions that take place if we add a carbonate. Again, we're going to start with 2+ ions. Again, we get a precipitate, and we get a metal carbonate. So you just need to remember that if you've got a 2+ metal ion and you add a carbonate, you're going to get that metals carbonate as a precipitate formed. However, something different happens if it's a 3+ ion that we're adding the carbonate to. So if you remember earlier, there was a difference in the pH between a metal 2+ hexa aqua ion and a metal 3+. So the pH of a metal 2+ was about 6, and the pH of a metal 3+ was about 3. That's a large difference in pH. And with a pH of 3, we've clearly got something now that is a weak acid. So we know from our carboxylic acids that when you react, we know that one of the tests for a carboxylic acid is hydrogen carbonate, sodium hydrogen carbonate, or sodium carbonate, and we see the fizzing, we get the effervescence, the carbon dioxide released, and that's exactly what happens here. We add a carbonate to our metal hexa aqua ion, that's a 3+ ion, and we get effervescence, and that is an indicator that we've got a 3+ charged ion. Again, this is just confirmation of that, really. So with a 2+ complex ion, we get a carbonate precipitate, but with a 3+ complex ion, we get the effervescence, the gentle fizzing, we get carbon dioxide produced. We get a different reaction. So now we have ligand substitution, and this is typically involves the addition of Cl- ions. And that's because what we'll actually get is a change in the shape of the complex ions. So typically most complex ions, or most of the ones that we've been looking at, are octahedral, so they have 6 coordinate bonds. If we have a ligand substitution with chloride ions, so say replacing water molecules, these chloride ions are much larger, and you can't fit 6 around the central metal ion. The maximum you can fit is 4, and with most metal ions that would result in a tetrahedral shape. So we'd be changing from an octahedral to a tetrahedral shape. So we have got cobalt here. If you remember what it said earlier about cobalt on the AQA guidelines or information, we weren't expected to know the colours of cobalt. But we've just got it here because it is a ligand substitution. It does give us a colour change. We can observe that, we can see that, and it's really just to illustrate the fact that we're going here from an octahedral complex ion to a tetrahedral complex ion, and we get a change in colour. Copper we are expected to know, so this time we have a ligand substitution reaction. The water molecules are being substituted for Cl- ions. Notice we're going from a 2+ charge to a 2- charge overall in the complex ion. We have a change in coordination number from 6 to 4. We have a change in shape from octahedral to tetrahedral, and we get a change in colour. Ligand substitution can occur with ammonia, although in most cases what we're really witnessing is hydrolysis and not ligand substitution. But there was one, if you remember, with copper that we did eventually get ligand substitution. There isn't a significant difference in the size of ammonia and water molecules, so we are not going to get a change in shape. So if we had octahedral to begin with, we're going to end with octahedral as well. And then this is the example that we saw earlier. So initially when we add the ammonia, we've got hydrolysis with precipitate being formed. So really we're just getting an OH bond breaking on the complex ion. But if we add excess ammonia, we then do get ligand substitution. So if you look at the final complex here, not sure if you can see that colour that well. But anyway, that final complex, it's octahedral, but we have got a ligand substitution. So we still have an octahedral complex. Probably the ammonias are in the sort of square planar plane, and we have the two water ligands vertical, so above and below, but it doesn't really matter, but we've got the ligand substitution. This is just a reminder of one of the things that might drive a ligand substitution, something that we can call the chelate effect. It all goes back to the thermodynamics topic we did about increases in entropy, or, well, really actually an increase in entropy of the universe, and that's really what delta G is giving us a sense of. So if delta G is negative, there is an increase in entropy in the universe. So we're focusing, when we're looking at these particles, 4 particles on the left for the chromium complex ion, 7 particles on the right for the second chromium complex ion. We are focusing there on the system, so we can see that there's clearly an increase in the entropy of the system, and we can see that on the second reaction as well. So remember though that delta G isn't just about the change in the entropy of the system, it's also about the change in entropy of the surroundings, and that is related to the change to the enthalpy change, to delta H. But in most of these instances, the change in enthalpy is, as it says here, negligible, because we're typically only replacing the same type of coordinate bond. You know, it might be with an oxygen, to a lone pair on an oxygen, or a lone pair on a nitrogen. So if we just look at the second one, with the EDTA, there are 6 water molecules around the central metal ion, so 6 water ligands. They all have an oxygen with a lone pair. That's what's forming the coordinate bond. In EDTA, there would be 4 oxygens forming that coordinate bond and 2 nitrogens. There is a difference, but that change in enthalpy is negligible, is small. It's not saying it's 0, it's just small. But the change in the entropy of the system, because of the change in the number of particles, is large. From 2 to 7 is a large increase. So we have a big increase in entropy. We're going to get a negative change in the Gibbs free energy in delta G, and that's essentially what's driving the ligand substitution reaction. Again, just a sort of summary of that, so by all means just sort of pause the video to read through it if you wish, but it's essentially what I've just been saying. And it is it is the main factor behind certain treatment for iron poisoning. So sometimes lead poisoning, for example, something that the medical profession might administer is EDTA. So that's it. That's the reactions of metal ions. It does require a lot of practice, I'm afraid. So you've got this video, you've got an extended PowerPoint. You've also got the the booklet. But really what you need to do now is to try and answer questions. So that's the next stage for you, and just let me know if you've got any queries. All right, thanks very much.